Hi everyone. Last time we did 7.1, which was about exponential equations and functions, and this one is going to be 7.3 about logarithmic functions and equations. So go click the link on Blackboard and get the notes and print them out, and then we can get started. Okay. So logarithmic functions have a special relationship with the exponential functions that we worked with in 7.1. And that relationship is that logarithmic functions and exponential functions are inverses of each other. So in exponential functions, we would have something like f of x equals a to the x, or I'm going to write b to the x, and our base would be b. And so logarithmic functions have bases too, and if we have a logarithmic function with base b, it's the inverse of the exponential function of base b. So the exponential function of base b would be f of x equals b to the x, and the logarithmic function of base b is f of x equals log, which we write just as log, and then base b would be written as a little subscript there, and then x on the inside. And so this is not log base b times x. It's not multiplication. It's like log is a function and it's like x is on the inside, like it's holding x. So we'll say log base b of x, not times. So whenever we have this relationship here, hold on, I'll highlight this one too. So logarithms and exponential functions and equations have this sort of property here, which we're going to use a lot in this section. So the thing I'm about to write is important and you need to have it in your mind. So if we have log base b of x equal to some mystery number, I'll write a question mark, then we can rewrite this as an exponential equation where it is x equals b to that power that's a question mark. So it's basically a way of rearranging the logarithm to be written as an exponent. So this b becomes this b, this x is the same as this x, and then our question mark is the same thing as the question mark there. So it's basically just rearranging it from one form to the other, and both of these equations mean the same thing. So a property of logarithmic functions is that their domain is restricted. Their domain is from 0 to infinity. So what that means is 0 to infinity are the only numbers that can be on the inside of a logarithmic function. These are the only numbers that you can plug in for x here. So negative numbers and 0 are not allowed. And then the range of a logarithmic function is negative infinity to infinity. So one thing that we're going to have to think about in this section is the inside of the logarithm can only be positive. So not negative, not 0. Okay. And so this property here, where we're rearranging the logarithmic function into an exponential function, here's like sort of an example of that. We have log base 2 of 16 equals 4. And so this equation is true, But one way we can see that it's true would be if we changed it into its exponential form. So we have, in this case, our x would be 16, like it is up here with the logarithm, x on the inside. Our b, or our base, would be 2. And then our question mark, or the number that's equal to, is 4. And so we can rearrange that to become 16 equals 2 to the 4th. So the same 3 numbers, just rearranged in a different order. And so that is an example of how this property up here works. Okay, so now we're going to talk about special cases of logarithms. So these are special logs that we're going to see a few times in this that are not written with a base. So the first one is ln of x, or the natural logarithm of x. So the base of this ln of x is e, and e is a number kind of like pi. It's not the same number as pi, but it's a number that's irrational like pi, and it has a lot of interesting and important properties. So ln, or natural log, is called the natural logarithm, and the number e is called the natural exponential. And e is approximately equal to 2.71828, but it goes on forever like pi does. So those numbers would keep on appearing in a unpredictable order. Then the other special case that we have is whenever we don't have a base written here. So this one is just log and it doesn't have anything there. So if it doesn't have the base written, we're going to assume that the base is 10. And this is just called the common logarithm. So if it just says log of x, just know that that means log base 10 of x. Okay. So there are 3 properties of logarithms here that might help you solve some of your equations fairly quickly, to just know these properties. And the first one is the log base b if we have a 1 on the inside, or we call that the argument of our log. So if 1 is on the inside, we'll think about what that equals, what this number has to be. So I'm going to set this equal to a question mark and try to solve it, and try to think of logically what that number would be. So if we use the property from before, where we change this from a logarithm to an exponential, then we should be able to write it as 1 equals b to our mystery power, question mark. And so now we're thinking the number b to what power equals 1. So with any number, we have that number raised to the 0 power is 1. So like 5 to the 0 would equal 1. 1 to the 0 would equal 1. Anything 1 million to the 0 power equals 1. So in this case, we would know that this power here, the question mark, needs to be 1. So in that case, log base b of 1 is, or sorry, if this question mark is a 0, then we equal 1. So log base b of 1 is equal to 0. Sorry, so if we want b to a power to equal 1, it needs to be b to the 0 power. Okay. So now, with the second property, we think, what do we have whenever our base and our argument are the same number, a? So I'm going to set that equal to our question mark and then rearrange to an exponential form. And so we have a equals a to the question mark power. So this a here is like the argument on the inside. This other a is like the base, and then our question mark is our question mark. So a being a to what power? We know, 3 equals 3 to the first power, 4 equals 4 to the first power. Anything is itself to the first power, so we know this question mark has to be 1. So whenever the base and the inside are the same, the log is 1. So now the third property would be, what if you had the base and then the inside is the same base but raised to a power of x. So log base a of a to the x equals something. We need to figure out what that something is. And so we use the property of exponents and logs to rearrange that one in the same way. So it becomes a to the x equals a to the question mark, where the base a goes to the other side, the question mark now becomes the power, and then the argument is a to the x is by itself. So now this one, we use what we learned in 7.1, the exponential property of equality, to say since we have the same base, a and a, the powers x and question mark would be equal to each other. And so now we know that log base a of a to the x just becomes x. So it's like you have this exponential on the inside of the log and this log on the outside, and it's like they cancel each other and you're just left with x. Okay. So those 3 properties may help in some of these equations to sort of get the answer a little bit quicker if we can just know those instead of having to work it out every time like this. Okay. So now what it wants us to do with these first examples are to evaluate these numbers. So we want them to actually like equal a number. So since we're saying them equal to a number, I'm going to just set it equal to a question mark and then solve for what that question mark would be by changing it to exponential equations instead of logarithmic equations, and then using the same methods that we used in the previous lesson, the exponential property of equality. So with this first one, we have, let's see, how did I do that? We have 256 as our argument, 16 is our base, and the question mark being the number on the other side. But we can rewrite this as 256 isolated. 16 is the base of the exponential, and the question mark is now the exponent. So just by using that property that I wrote with a star earlier up here, this property here. Okay. So now that we have that, we're going to try to figure out what this question mark is. So before, we would try to find the base, a common base that we can use. So 256 is equal to 16 times 16, which is 16 squared. So since 256 is 16 squared, and this side here is already written as 16 to a power, our base can be 16. So we'll rewrite this side as 16 squared, keep this side the same. And then since we have the same base, we can set the powers equal to each other. And so our answer for all of these types of examples is just going to be a number. So we're just going to write 2 as our answer, because when we set it equal to our mystery number, we got that our mystery number was 2. All right, so that was the first example, and now I'll work example 2. So yet again, we're trying to figure out what this equals. So we'll set it equal to a question mark and then solve for our question mark. We can think of the question mark just like any other variable. If it was X or Y, I just chose a question mark because I've used a lot of the letters like A and B already, and then X and Y, and I think it might get confusing if I use them for too many things. So I'm just using question mark instead. Okay. So now we've got log base 4 of 1 equals question mark. But we can think about one of our special properties for this one and make it pretty easy. This would be like the property number 1. So this first property here, where if we have a 1 on the inside, then we have our answer is 0. So since we have a 1 on the inside, we can automatically say that log base 4 of 1 equals 0. And then we don't have to work that out every time. But if you did want to work it out, then you would you would rearrange it to become an exponential. So it would become 1 equals 4 to the question mark. And you would say, well, 4 to the 0 equals 1. So it would become our question mark equals 0. So in this case, 0 is our answer. But we didn't have to work this out like this. If we wanted to, we could just know that if 1 is the argument or the number on the inside of the logarithm, then it's always 0. Okay, so for example 3, we have our first natural log, ln, and ln has base e. So we're going to write it as ln. Instead of ln, I'm going to write it as log with base e equals the 8th root of e to the 3rd. Okay. So 8th roots can be written as a power of 1/8. So just like if we have square root of x, we can write that as x to the 1/2. If we have the 8th root of x, then we can write it as x to the 1/8. So I'm going to rewrite this instead of the 8th root of e to the 3rd. I'm going to write it as log base e, and then this is going to be e to the 3rd to the 1/8 power. Okay, so we also know that if we have a power, e to a power raised to another power, that we can multiply those. So this can be written as log base e of e to the 3 times 1/8, which becomes 3/8. And then this is property number 3. It is just like whenever we had this log base a of a to a power. We have the base and then the argument raised to a power are both, it's the same number. So in this case, we have e and then e raised to a power. And our answer should just be that power. So here we have log base a of a to the x equals x. And so we just end up taking the power of whatever is on the inside. So log base e of e to the 3/8 is just equal to 3/8. So 3/8 ends up being our answer for number 3. Okay. So now with number 4, we have log base 1/4 of 64. So I'm going to set it equal to a mystery number and solve for that. And I'm going to first rearrange it to the in exponential form. So 64 equals 1/4 to our mystery power question mark. So I'm just highlighting every time so you know which property that I'm using there. Okay, so now we will try to use the exponential property of equality by setting them both as the same base to a power and then setting the powers equal to each other. So 64 we know is equal to 4 times 16, which is equal to 4 times 4 times 4, which is 4 cubed. And 4 is just 4 to its own power, but here we have 1/4. So 1/4 is like 1/4 to the first power. So what we can do is we can put the 4 in the top of the fraction as a -1 power. So the 64 becomes 4 cubed from here. And then 1/4 equals 4 to the -1. So we can write as 4 to the -1 question mark. Okay. So here we have them both written as base 4. And I'm going to erase this so I'll have room. And we need this to just be 1 power. So since our question mark is just a variable, we can multiply it by -1, and that's just fine. We'll have 4 to the 3rd, and then we'll have 4 to the -1 times question mark, so it can be a negative question mark. That's fine, the question mark is just a variable. And then since we're the same base, we can set 3 equal to the negative of our question mark. And then if we want the question mark by itself, we can divide by that negative, or divide by -1 on both sides. And we end up with -3 equals our question mark. So our final answer in this case ends up just being -3. All right. So that is the first 4 examples. Now we're going to work a few different examples where we are solving equations. So with these, it was just evaluation. We did make equations with a few of them by saying them equal to question marks, but now we're going to be given equations where they already are things equal to each other, and we'll be solving for x. Okay, so we're going to solve these equations, and then we will have the answer as either a fraction or a decimal rounded to 2 spaces. So since we might end up having to use decimal numbers here, go ahead and if you have a calculator, get that out, because we'll be plugging things into a calculator, and there's a special way that you have to plug in some logarithms. Okay. So we'll just go ahead and start with the first example. Log base 2 of 4 to the 4x equals 4. So the first thing I'm going to do is I'm going to rewrite this as, hold on. I'm going to rewrite this as an exponential equation and then solve it that way. So 4 to the 4x equals 2 to the 4th. And so everything just gets rearranged just the way we've been doing the entire time. And now we can do the exponential property of equality by setting these equal to the same base, or rewriting these with the same base and then setting the exponents equal to each other. So our base in this case is 2, because 4 equals 2 squared, and then this side already has a base of 2. So we can write as 2 squared to the 4x equals 2 to the 4th. Here, let's multiply these powers together and get 2 to the 8x equals 2 to the 4th. And then we can just set the powers equal to each other. 8x equals 4 and divide by 8. Well, we got x equals 4 over 8. But when we simplify that, we end up with x equals 1/2. Because 4 over 8 is 1/2 once it's simplified. Okay. So that is just how we solve the first equation. We'll first just do the property that I used with a star, do the exponential property of equality, and get our answer for x. Okay, so we'll move on to number 6. Okay, so number 6, the first thing we'll do is we will rewrite it as an exponential equation. So 5x equals 4 squared. So 5x moves here. The 4 becomes our base, and our 2 becomes our exponent. And then we can try and solve it from here. So 4 squared is 4 times 4, which is 16. So we end up with 5x equals 16. And then we divide by 5. And we get x equals 16 over 5. So that one we ended up not having to use the exponential property of equality because we didn't end up having an x. After we changed it to an exponential function, or in its exponential form, we end up not having an x in the exponent of either side of the equation. It just ended up being just a regular polynomial equation. Okay. So here, let's work with number 7. So with number 7, we know that natural log is log with a base of e to the x. And then we have that equal to 20.8. And so this should remind you of property number 3 of the 3 special properties of logarithms that we have, where it's log base a of a to the x equals x. And so here we have our base is e, and the inside we have e to the x. And so in that case, we have log base e of e to the x just becomes x. And so the side stays 20.8, and we already have x solved for. So that one was a pretty quick one. All right. So now, number 8, we will have to rewrite this one as in its exponential equation form. And so in this case, we'll write 2x minus 4 equals 2 to the 6th. And so our power becomes 6. Our base is 2, and then the argument goes by itself on this side. Okay, so now 2 to the 6th power is 2 times 2, 2, 2, 2, 2. So we have 2 times 2 times 2 is 8, and we have that twice, so that should be equal to 8 times 8, which is 64. And so 2 to the 6th power is 64 on this side. We have 2x minus 4 on the other side. And we can solve that easily by just adding 4, being 2x equals 68, and then dividing by 2. We get x equals 34. Okay. So that is the last example in this section. And if there are any questions or if you found anything on Hawks that you would like to have worked out, feel free to come to the Zoom sessions and ask about those. The links are on Blackboard. If you're in my class, you can email me. If you're in someone else's class, you can email any of your, like whoever your teacher is. And just let me know if there are any questions about this. And have a good day.